Okay, 2.21. This is pretty horrid mathematically to do, but part A is still relatively simple, so we'll start off nice and easy before ramping up to the more painful stuff in the later parts. We have a Gaussian wave packet. First thing we're asked is to normalize psi of x comma 0 by finding A. So that's easy enough. We recognize the fact that by the integral from negative infinity to infinity of magnitude a squared e to the negative 2ax squared dx has to equal 1 due to the fact that this is a probability distribution. Then we recognize that this is a Gaussian, so we take advantage of the ERF function, which states that ERF of z is equal to 2 over the square root of pi times the integral from 0 to z times e to the negative t squared dt. So all we have to do here is we have to use a change of integrals, or not change of integrals, a change of variables. So we say u equals square root of 2a times x. That means du equals square root of 2a dx, which means that dx equals du over square root of 2a. So what we have left is magnitude a squared, integral from negative infinity to infinity of e to the negative u squared times du over square root of 2a. And this has to equal 1. So magnitude a squared, integral from negative infinity to infinity of e to the negative u squared du equals square root of 2a. From here, we go back to this ERF function, so we say that, okay, square root of pi over 2 times ERF of z is equal to the integral from 0 to z of e to the negative t squared dt. So we want to get the zeros in, so this can be rewritten as magnitude a squared times the integral from negative infinity to 0 of e to the negative u squared du plus the integral from 0 to infinity of e to the negative u squared du. And this is equal square root of 2a. Finally, we switch sort of this integrand around by adding a negative. So we have magnitude a squared, negative integral from 0 to negative infinity of e to the negative u squared du plus the integral from 0 to infinity of e to the negative u squared du. And this is equal to square root of 2a. And then we just replace this with the ERF functions. So this is going to give us magnitude a squared times negative ERF of negative infinity multiplied by square root of pi over 2 plus ERF of just positive infinity times square root of pi over 2. So the ERF of negative infinity and positive infinity respectively are just negative and positive 1. So this is going to give us magnitude a squared multiplied by negative 1, which is going to give us just positive 1. So this is just going to be square root of pi over 2. And then this is just going to be 1. So we have plus square root of pi over 2. And this equals square root of 2a. So what we have is magnitude a squared times square root of pi is equal to square root of 2a, or magnitude a squared is equal to square root 2a over pi, or a is equal to 2a over pi to the power of 1/4. So if we write this out fully, then we have psi of x comma 0 is equal to 2a over pi to the power of 1/4 multiplied by e to the negative ax squared. And that is part A, which is the easiest part of this problem, and now we instantly move on to sort of mathematical hell, if you will. All right, this is where the pain starts. So we are asked to find the general wave function psi of x comma t, and we're given a hint to do how to do integrals of a very specific nature that we'll encounter multiple times throughout this calculation. So let's ignore this for now and just actually do the setup. So we know from the Fourier transforms that we've described in this section that psi of x comma t is just equal to 1 over square root of 2 pi times the integral from negative infinity to positive infinity of phi of k times e to the power of I times kx minus h bar k squared over 2m multiplied by t. And we close this off by dx, and we know that phi of k can become solved as 1 over square root of 2 pi times the integral from negative infinity to positive infinity of psi of x comma 0 times e to the negative I kx dx. And now the first part of this problem, for the first part of part B, we are going to plug psi of x comma 0 in and solve for phi of k. So what is this going to equal? This is going to equal 1 over square root of 2 pi, and then we have this normalization factor of 2a over pi to the power of 1/4 at the front, and then we're multiplying by the integral from negative infinity to positive infinity of e to the negative ax squared times e to the negative ikx dx. And what we see here is that this looks very similar to this form right here. So let's try to massage this into something of this form of e to the negative ax squared plus bx. So what we have is 1 over square root of 2 pi. Actually, you know what? I'm just going to call this, in order to save my wrist a little bit, I'm just going to refer to this as a constant that I'm going to call a, multiplied by the integral from negative infinity to positive infinity of e, and then let's see, this is going to be negative, which I'm going to move out at the front, and then we have ax squared plus ikx dx. So what we're doing here is we've just redefined this exponential in terms of this form, which is what we've encountered. We don't really know how to solve this off the top of our head, so Griffiths has kindly provided us a hint via a method known as completing the square. So what we're going to do is we're going to redefine these variables. So a here is clearly just equal to a, and b is equal to ik. And what we're supposed to do is we're supposed to do something called completing the square, where we define this new variable y, which equals this, and then we note that this term, which is what this is, can be re-expressed in terms of y. And if we do that, this is just a constant, and y squared is the thing that actually matters. We can do a change of variables to y, and this is going to give us a Gaussian, which we can solve. So let's just do that. So first off, let's define y. So y is equal to the square root of a, and in fact, you know what? Let's do this in a different color, just so my eyes don't go blind from looking at this massive wall of black text. Y is equal to the square root of a multiplied by x plus b over 2a. And luckily here we have a is just equal to a, so we don't have to do any substitutions of that. We just have to substitute b. So this is going to equal square root of a times x plus ik over 2a. Now we note that ax squared plus bx is equal to y squared minus b squared over 4a. So this is suggesting that we use u sub basically and change to y. So let's also define a dy. So dy is going to equal just, let's see, the only x term is at the front here, so this term just goes to 0. What we have left is just square root of a dx. So therefore dx is equal to dy over the square root of a. So if we plug this in, what we have, and let's write this next part in blue, so ax squared plus bx, or in this case, it might be even better to just write it in terms of this. So ax squared plus ikx is going to equal y squared minus b squared over 4a. So b squared, well, b is ik, so b squared is going to be just negative k squared. So this negative changes to a positive, plus k squared over 4a. So if we rewrite everything, what we're going to get is that this is going to equal the same constant a at the front, which I don't want to rewrite, multiplied by the integral from negative infinity to positive infinity. And what we see here, first off, if we change variables to y, if x goes to, because everything else here is a constant, so if x goes to infinity, y also goes to infinity, and if x goes to negative infinity, y also goes to negative infinity. We don't have to worry about changing our bounds, luckily. And we have e to the negative y squared plus k squared over 4a, and then we have dy over square root of a, and this is how we close our integral. And now our integral is in terms of y, which is a very nice sort of thing because everything else is a constant. We don't have to worry about it. Let's redefine this. So a, and then this is going to be e to the negative k squared over 4a times our integral from negative infinity to positive infinity of e to the negative y squared times dy over square root of a. Once again, we use the ERF function, or we take advantage of the ERF function. So I'm going to write this in green. We know that ERF of z is equal to 2 over square root of pi times the integral from 0 to z of e to the negative t squared dt, or also rewriting this in the more preferred form, square root of pi over 2 times erf of z is equal to the integral from 0 to z of e to the negative t squared dt. Now let's rewrite this in terms of that. So we have a over the square root of a times e to the negative k squared over 4a. And then we have this negative integral from 0 to negative infinity. I'm just going to do this right away and switch the integrands from bottom top to top bottom of e to the negative y squared dy. And then we have plus integral from 0 to infinity of e to the negative y squared dy. These are equal to square root of pi over 2 of ERF of negative infinity and positive infinity respectively. Those ERF functions go to positive and negative 1 at positive and negative infinity respectively. So this is just going to be equal to a over square root of a times e to the negative k squared over 4a. And then we have square root of pi over 2 plus square root of pi over 2. This is just going to give us square root of pi. So this is a square root of pi over a times e to the negative k squared over 4a. And now we can plug a back in. So we know that a is going to equal this. So let's just take this and copy paste it and move it down here. So what we have is equal to a times this times the square root of pi over a times e to the negative k squared over 4a. The square roots of pi cancel. So this is just going to be 1 over the square root of a, and then we cancel out the square root of pi. Let's just write this out in a little bit of a neater way. 1 over square root of 2a times 2a over pi to the power of 1/4, and then e to the negative k squared over 4a. And with that, once again, remember we're solving for phi of k, so this is equal to phi of k. And then we can move on, and now we can solve for psi of x comma t. Okay, now let's move on to actually solving psi of x comma t. We plug phi of k back in, and what we're going to get is that psi of x comma t is equal to 1 over square root of 2 pi times 1 over square root of 2a times 2a over pi to the power of 1/4. And then we have our integral from negative infinity to positive infinity of e to the negative k squared over 4a times e to the ikx times e to the negative I h bar k squared over 2m times t. And we're closing all this with dk. And the reason why I'm writing that like this is that this is also can be sort of massaged into the same form as the hint gave, which is e to the negative ax squared plus bx, but this time in terms of k, and we have to do this whole completing the square thing all over again, but this time in a much more complicated sort of setup. So let's rewrite this a little bit and make this a little bit neater. This can be rewritten as 1 over 2 square root of pi a times 2a over pi to the power of 1/4. And once again, I'm going to do the same thing and redefine this just as a constant to save my wrist a little bit. And then we have an integral from negative infinity to positive infinity. And we want to collect terms. So we have two k squared terms. So let's write this e to the k squared of, let's see, negative 1 over 4a minus I h bar t over 2m. Is that correct? K squared, negative 1 over 4a minus I h bar t over 2m. Yes, that is. And then we have plus e, or not e, plus k times ix. And then this is all closed with dk. So we can sort of massage this a little bit more, because remember, we're trying to get a negative out at the front. So this can be rewritten, and then I'm just going to write a as our constant from now on, from negative infinity to positive infinity. E to the negative of, let's see, what is this going to give us? If we take out a negative, then this is, instead, it might be better to write in square brackets. This is going to give us 1 over 4a plus I h bar t over 2m times k squared, and then subtracted by ix k. And that should give us the same thing. If we multiply the negatives do that, and the positives, the two negatives cancel out, make a positive. Yes, okay, this is the form that we want. So what we've done here is our a term is effectively equal to 1 over 4a plus I h bar t over 2m, and our b term is equal to negative ix, because remember, we're trying to get it into this form of ax squared plus bx, or ak squared plus bk. So now we have to do the thing, or the whole y substitution. So I'm going to write this in blue. So we can say we're going to let y equal square root of a times x plus b over 2a. So we do that, and this is going to equal the square root of 1 over 4a plus I h bar t over 2m. And then we have, instead of x, we're going to be replacing it with k, because that's our variable of interest. So I should actually erase this and replace it with k as well. And this is going to be subtracted by ix divided by 1 over 2a plus I h bar t over m. Okay, and from here we want to do sort of a y substitution. So dy is going to equal the square root of 1 over 4a plus I h bar t over 2m times dk. And now we use the substitution, and we recognize that this term right here can be rewritten. So we're going to recognize that, let's see, ax squared plus bx, which is 1 over 4a plus I h bar t over 2m times k squared minus ixk can be rewritten as y squared minus b squared over 4a, or y squared, and then let's see, b squared is equal to I squared x squared, or just negative x squared. So minus b squared is going to be plus x squared over 1 over a plus 2I h bar t over m. And now we substitute this over. So this is going to give us psi of x comma t is equal to a times our integral from negative infinity to infinity of e to the power of negative y squared minus x squared over 1 over a plus 2I h bar t over m. And then we close this off with a dy over the square root of 1 over 4a plus I h bar t over 2m. And from here, this is just, once again, a Gaussian that we've solved many times before. We can isolate out sort of these constants at the front that don't really matter. And we plug in a again, so we know what a equals. A is this right here. Let's just copy this and get rid of the a term, or get rid of the sort of the a bracket that I've marked out at the bottom. And then we're multiplying by 1 over the square root of 1 over 4a plus I h bar t over 2m. And then what do we have? We have this extra exponential, e to the power of negative x squared over 1 over a plus 2I h bar t over m. And then we have our integral from negative infinity to infinity of e to the negative y squared dy. This is a Gaussian integral, just equals the square root of pi. So the square roots of pi cancel, so what we're left with is 1 over 2 square root of a times 2a over pi to the power of 1/4 times 1 over the square root of 1 over 4a plus I h bar t over 2m. And then e to the negative x squared over 1 over a plus 2I h bar t over m. And technically, we have our answer. Now, we might technically have the correct answer, but this isn't the answer that Griffiths wants. We can rewrite this into a bit of a neater format by using the suggested answer that Griffiths gives us, which is that psi of x comma t is actually equal to 2a over pi to the power of 1/4, and then multiplied by 1 over gamma times e to the negative ax squared over gamma squared, where we've defined gamma to equal the square root of 1 plus 2I h bar at over m. Now, thankfully, this conversion actually isn't that difficult to do, because immediately we see that there's a 2I over pi to the power of 1/4, so we don't have to do anything with that. And then we have an exponential, so this is probably going to simplify to this, and we have this these two constants multiplying, and these are probably going to become 1 over gamma. So immediately, the first instinct is to combine sort of the two constant terms right here. So if we do that, what we're going to get is 2a over pi to the power of 1/4, which we're going to move to the front, times 1 over, and then this is just square root of 4a, right? So this is square root of 4a multiplied by 1 over 4a plus I h bar t over 2m. And then we have e to the negative x squared over 1 over a plus 2I h bar t over m. So this is going to drop off into square root of 1 plus 2I h bar at over m. And that's exactly what, this is just 1 over gamma, because gamma equals this. Now, for this exponential side, we know what it's supposed to look like, so let's just sort of take gamma and multiply, let's just square gamma and then like take it in the denominator and multiply by a and see what we get. So what is this going to become? So gamma squared is equal to 1 plus 2I h bar at over m. And if we want to turn this into a fraction, this is just equal to m plus 2I h bar at all over m. So that means 1 over gamma squared is equal to m over m plus 2I h bar at, and a over gamma squared is equal to am over m plus 2I h bar at. So what this means is that e to the negative a x squared over gamma squared is really just equal to e to the power of negative am over m plus 2I h bar at x squared. So if we can get this exponent into this form, then we've finished the problem. Let's try to do that. So currently we have 1 over a plus 2I h bar t over m, and we're going to try to get it into this constant at the front here. So immediately I'm going to combine terms. So this is going to give 1 over, and then let's see, what do we have? Multiply this side by m over m, and multiply this side by a over a. So we have m plus 2I h bar at over am. Is that correct? M at the top, m at the bottom, a at the top, a at the bottom, so m plus 2I h bar at. Yeah, and taking the reciprocal of this is going to give us am over m plus 2I h bar at, and that's exactly what we want. That's what this equals. So therefore, we have the answer. Psi of x comma t does indeed equal everything written here, with gamma being defined as this. And with that, we are done with part B. Okay. Part C, we want to find the magnitude squared of psi of x comma t. So we have everything that we've already defined up here, and we can just sort of take this and take the magnitude squared, because we have everything in this nice format in terms of gammas. So we can just add on a factor that gamma star is equal to square root of 1 minus 2I h bar at over m. So what's this going to give us? So, magnitude psi of x comma t squared is going to be just equal to, we have the 2a over pi to the 1/4 term, which squares itself because there's no imaginaries here. And then we have 1 over gamma times 1 over gamma star, and then e to the negative ax squared over gamma squared times e to the negative ax squared over gamma star squared. And we just have to sort of plug everything in. So this is going to give us, let's see, square root of 2a over pi. And then we have 1 over gamma times gamma star. So what's that going to give us? Gamma times gamma star is going to equal the square root of 1 plus 2I h bar at over m. times 1 minus 2I h bar at over m. These are just complex conjugates of each other, so they multiply out to become real. This is going to give us the square root of 1, and then minus 2I h bar at over m plus 2I h bar at over m. Those two cancel. What we're left with is plus 4 h bar squared a squared t squared over m squared. So if we take the sort of reciprocal of this is going to give us 1 over, or whoops, this is still in red, let's write this in black, 1 over the square root of 1 plus 4 h bar squared a squared t squared over m squared. Close this off, and then we have e to the negative, and in fact this can be combined as well, so we can do negative ax squared of 1 over gamma squared plus 1 over gamma star squared. So what does this equal? Let's simplify this out as well. So gamma squared is equal to 1 plus 2I h bar at over m. So we want to collect like terms, since this is going to just be m over m plus 2I h bar at. So 1 over gamma squared is going to equal m over m plus 2I h bar at. Similarly, gamma star squared is going to equal 1 minus 2I h bar at over m, which is going to equal m over m minus 2I h bar at. So 1 over gamma star squared is going to equal m over m minus 2I h bar at. If we want to combine these two, then 1 over gamma squared plus 1 over gamma star squared is going to equal m over m plus 2I h bar at plus m over m minus 2I h bar at. We just have to combine these, so what we have is m plus 2I h bar at times m minus 2I h bar at, all divided by m times m minus 2I h bar at plus m times m plus 2I h bar at. These bottom terms are complex conjugates, so they're going to cancel out very nicely. At the bottom we get m squared plus 4 h bar squared a squared t squared. At the top we have, let's see, these two lower terms, so m times negative 2I h bar at and m times positive 2I h bar at both cancel out, so we're left with m squared plus m squared, so this is just 2m squared. So let's rewrite everything. Then magnitude of psi x comma t squared is going to equal, let's see, square root of 2a over pi times 1 over the square root of 1 plus 4 h bar squared a squared t squared all over m squared. And then we're multiplying by e to the negative ax squared times 2m squared over m squared plus 4h bar squared a squared t squared. And this problem specifically wants us to write this in terms of omega. So if we do that, let's introduce this new variable, omega, which equals the square root of a over 1 plus 2h bar at over m squared. And we can sort of massage this a little bit. So immediately what we see here is that this can be rewritten as 1 over the square root of 1 plus, let's see, 2 h bar at over m squared. So we also have a square root of a at the front here. So we can say magnitude psi squared is equal to square root of 2 over pi. If the square root of a moves to the denominator or the numerator, then this just becomes omega. And then we have e to the, and then we have this. So this sort of seems like we can modify this a little bit as well. Let's see. So omega squared, because there's no square root here, so that implies that we should just take the square. So omega squared is going to be it's going to be a squared over 1 plus 2h bar at over m squared. We can rewrite this as sort of negative x squared times 2m squared a over m squared plus 2h bar at squared. And then there's nothing necessarily stopping us from moving the m squared to the bottom, so this is going to be negative x squared. If we multiply by 1 over m squared, then this is going to be 2a over 1 plus 2h bar at over m squared. So what we can say is, well, from here, there's nothing stopping me from just rewriting this as omega squared over a, which is going to give us a over 1 plus 2h bar at over m squared. So if we write it like that, then this is just equal to negative, let's see, yeah, so this is just 2 times omega squared over a x squared. So if we move this down, then this is e to the power of negative 2 omega squared over a x squared, and this is sort of just our answer. Apologies, I just realized I made a bit of a mistake here. When we take omega squared, there's no squared on a, so it's not omega over a. Omega squared just equals this, so so this is just 2 omega squared x squared, actually. So get rid of the a at the bottom. Okay, and this is the correct answer. Okay, the next part of part C is that we want to see what happens to magnitude psi squared as sort of time grows. So we start at t equals 0 and we effectively go to t equals infinity. So let's analyze the two limiting case scenarios. So the only t dependence here is in omega, so let's analyze how omega depends on t. So the limit as t goes to 0 for omega is going to equal the square root of a over 1 plus, and then we just have 0. So omega just goes to square root of a. In contrast, if t goes to infinity for omega, then what we're going to get is square root of a over 1 plus infinity. So this is just going to go to 0. So we have, the problem here is that we have this this a term that we don't know what it is. A sort of depends on sort of the setup for our problem. Depends on like initial conditions, boundary conditions, whatever they may be. So in this case, just for simplicity, let's suppose that a is just equal to 1, in which case omega goes from 1 at t equals 0 to 0 at t equals infinity. So what we can do is we can just graph magnitude psi squared at 3 different values of omega and see how it transitions. So suppose we graph suppose we graph magnitude psi squared at omega equals 1, 0.5, and 0. So this is what we're doing is that since omega goes from 1 to 0, we're analyzing sort of 3 points. T equals 0, which is omega equals 1. T equals some positive value between 0 and infinity, which is 0.5. And then t equals infinity, which is at 0. So if we do that, what we'll see on a graph of sort of x versus magnitude psi squared is that the t equals 1 case just looks like a standard Gaussian, something like this, or the t equals 0 case. So this is t equals 0, or not t equals 0. It'd be more accurate to say this is omega equals 0. And we can graph, if you graph out omega equals 0.5, it looks like just a slightly sort of flattened Gaussian, something a little bit flatter. So this is omega equals 0.5, and then at omega equals 0, where magnitude psi squared just equals 0 because of the 0 term at the front here. So what that looks like is it's just a flat line at x equals 0 or at y equals 0. So this is going to be omega equals 0. So what we see is that sort of it starts as a very nice sort of ideal Gaussian curve, and over time this wave function flattens out, sort of getting like flatter but also fatter, until eventually in the limiting case of t going to infinity, in which case it just becomes 0 everywhere. Right. Okay. Welcome to the hell that is part D. The hardest part is going to be the expectation value of p squared, because we're going to have to take the derivative of this horrible mess of a wave function twice. So I've set up sort of all of the initial stuff that we already know here. We're going to do x and x squared first, because those are easy. We already know magnitude psi squared, so it's just a matter of plugging these in. Let's just do that right away. So the expectation value of x is going to equal the integral of magnitude psi squared x dx, going from negative infinity to positive infinity. And what we have here is just going to be, so let's see, square root of 2 over pi times omega, because omega has no x dependence, times the integral from negative infinity to infinity of x e to the negative 2x squared omega squared dx. Thankfully, this is the easiest one of the lot. E to the negative 2x squared, and I don't know what happened here, but my omega squared came down instead of being at the top, like it's supposed to be. Anyway, this is an even Gaussian function. X itself is an odd function. An odd function times an even function is an odd function, and a symmetric integral of any odd function is always going to be 0, so the expectation value of x is automatically just 0. The harder one, x squared, is going to be the integral from negative infinity to infinity of mag psi squared x squared dx. This is going to be square root of 2 over pi times omega times the integral from negative infinity to infinity of x squared e to the negative 2 x squared omega squared dx. To solve this, we use the traditional method of integration by parts and taking advantage of sort of the fact that we can rewrite this as x times x e to the negative 2x squared omega squared. So what we can say is that, okay, recognize the fact that d by dx of e to the negative 2x squared omega squared is equal to negative 4 omega squared times x times e to the negative 2x squared omega squared. So what this implies is that x e to the negative 2x squared omega squared is sort of equal to negative 1 over 4 omega squared d by dx of e to the negative 2x squared omega squared. So we can rewrite the expectation value of x squared to equal square root of 2 over pi times omega at the front, and then our integral from negative infinity to positive infinity of x multiplied by negative 1 over 4 omega squared times d by dx of e to the negative 2x squared omega squared dx. Then we move all the constants out, and what we have left is negative square root of 2 over pi times 1 over 4 omega. And then we have our integral from negative infinity to infinity of x times d by dx of e to the negative 2x squared omega squared dx. Okay, now we can use u sub. So what do we have? We have u is equal to x, so du is equal to dx. dv is equal to d by dx of e to the negative 2x squared omega squared dx. And so v is going to equal e to the negative 2x squared omega squared. And what we have when we use u sub is that the expectation value of x squared is going to equal negative square root of 2 over pi times 1 over 4 omega. And then what is this going to become? uv, which is x e to the negative 2x squared omega squared, which goes to 0 automatically because this is a Gaussian that goes to 0 exponentially versus, you know, an x that goes to infinity linearly. So uv minus integral v du. So minus the integral from negative infinity to infinity of v du, which is e to the negative 2x squared omega squared dx. The two negatives cancel out. What we have left is just a standard Gaussian integral, square root of 2 pi over 1 over 4 omega times the integral from negative infinity to positive infinity of e to the negative 2x squared omega squared dx. We use u sub. U is going to equal, let's see, x omega root 2. So du is going to equal omega root 2 dx, which means that dx equals du over omega root 2. So then this is going to equal square root of 2 over pi times 1 over 4 omega, integral from negative infinity to positive infinity, of e to the negative u squared. Is that correct? U squared is x squared omega squared 2. Yes, that's correct. Okay. And then multiplied by du over omega root 2. So the root 2's cancel, and what we have left is 1 over square root of pi times 1 over 4 omega squared, and then this integral, which becomes just square root of pi, as we've seen many times before. So we have just 1 over 4 omega squared. If we want to rewrite this in terms of what it actually equals, well, we have that omega is equal to this. So this actually equals, let's see, omega squared is a over 1 plus 2 h bar at over m squared. So 1 over omega squared is equal to 1 plus 2 h bar at over m squared over a. So 1 over 4 omega squared is going to be 1 plus 2 h bar at over m squared over 4a. And that is the first part of probably like 3 or 4 parts in this problem. Okay, now starts sort of the real meat of this problem, which is to find the p-hat expectation values. So we have to take the x derivative of this function. So let's start with that immediately. So d by dx of psi is going to equal 1 over 2 root a times 2a over pi to the power of 1/4 times 1 over 4a plus I h bar t over 2m to the power of negative 1/2. And then we have e to the power of, well, no, actually we actually have to take the derivative of this. So negative 2x over 1 over a plus 2I h bar t over m. And then we're multiplying by e to the negative x squared over 1 over a plus 2I h bar t over m. Next, we want to take the second derivative of this. So d2 psi by dx squared is going to equal the same thing at the front. So 1 over 2 root a times 2a over pi to the power of 1/4, 1 over 4a plus I h bar t over 2m. And then, and also, you know what, I just realized this looks like a minus sign, so let's throw parentheses on there to indicate that it's multiplication to the power of negative 1/2. And then we have negative 1 over 1a plus 2I h bar t over m. You know what, let's do 2. And then we multiply it by product rule, box prime times triangle plus triangle prime times box. So this is e to the negative x squared over 1 over a plus 2I h bar t over m. And then, oh god, okay, this is going to be minus, let's see, 2x squared over 1 over a plus 2I h bar t over m, I think. Negative 2x, yeah, 2x squared over, yeah, and then e to the negative x squared over 1 over a plus 2I h bar t over m. Like that. Okay, let's do psi. Let's do p hat first. So the expectation value of p is going to be equal to, you know, the integral from negative infinity to infinity of magnitude psi, or not even magnitude. In this case, it's going to be psi star times d by dx of psi. So we actually, thankfully, don't even have to do this fully, because what we sort of see here is that obviously there's imaginary terms that differ, but the main point here is that, you know, psi star multiplied by the derivative of psi is it's gonna have this Gaussian function, and this is even no matter what. So what will happen is that if we derive it, then what we have is we're gonna get this extra x term at the front, and that's an odd function. So automatically, for the same reason that sort of the expectation value of x equals 0, the expectation value of p is also going to equal just 0. This is really a very big pain to write because of how long this turns out to be. But hopefully you sort of see how, like, you sort of see it in that sort of, this derivative gives you x times e to, like, whatever this crap is, and then you have e to the power of the negative of that same crap up here. So these two multiply, all that does is add a factor of 2 at the final product, and we have an extra term of x at the front. So it doesn't matter what the junk is on the left, all these constants, they don't matter. What matters is that our final thing looks like something like x times e to the negative x squared. And the point for that is that since e to the negative x squared is even, and x is odd, the resulting function is odd, and the resulting integral is just a 0. The painful part is the expectation value of p squared, which as soon as I have a moment to catch my breath, I will go over. Okay, so a bit of a mistake in the p ones. There's a negative I h bar term at the front, but that doesn't really matter because that's just constant. Let's do p squared next. So this is going to be, let's see, negative I h bar, the whole thing squared is going to give I squared h bar squared, which is negative h bar squared times the integral from negative infinity to infinity. And then we have everything that gets multiplied. So let's start by just taking the square of all of this real stuff at the front. So that's going to give us 1 over 4a multiplied by the square root of 2a over pi. And then we have these imaginaries. So this is going to be 1 over the square root of 1 over 4a plus I h bar t over 2m. And then we're multiplying this by 1 over the square root of 1 over 4a minus I h bar t over 2m. And then we have the exponentials. So this is going to be e to the negative x squared over, and we want the sort of, and this negative is not in a very good place. So let's rewrite that real quick. Negative. Okay, so we want psi star first at the left. So this is going to be 1 over a minus 2i h bar t over m. Is that correct? 2i h bar t over m, yeah. And then multiplied by the second derivative of psi with respect to x squared dx. Well, actually, this isn't entirely right because we've already sort of multiplied all of these front terms. So let's just call it like psi with an overline to represent the fact that we've sort of already included everything here up to here. So what's that going to give us? Negative h bar squared, 1 over 4a times square root of 2a over pi. And then 1 over, and then these terms are just going to become like 1 over 4a squared plus h bar t over 2m squared. And then we have this term at the front. So the negatives are going to cancel out. So we have 2 over 1 over a plus 2i h bar t over m. And then we have our integral from negative infinity to infinity of e to the negative x squared, 1 over a minus 2i h bar t over m. And then multiplied by this mess, which is e to the negative x squared, 1 over a plus 2i h bar t over m, subtracted by 2x squared, 1 over a plus 2i h bar t over m. I'm running out of space. E to the negative x squared 1 over a plus 2I h bar t over m. And I'm just gonna do my best. Okay, we can factor that out and we can do some simplification here. So this is gonna give us what? H bar times 1 over 4a times square root of 2a over pi times 1 over square root of 1 over 4a squared times h bar t over 2m squared. And then we have, so the 2 at the top cancels out with the 4 to make 2a. And then we have 1 over a plus 2I h bar t over m. And then we have our integral from negative infinity to infinity. And we're going to distribute out these exponentials. It's going to give us e to the, let's see, negative x squared, and then 1 over a minus 2I h bar t over m. And then plus 1 over a plus 2I h bar t over m. And then 1 minus 2x squared over 1 over a plus 2I h bar t over m. And then we can actually close it off with a dx this time. Last time we ran out of room up here. And yeah, this is a pretty painful thing to have to work through. So let's sort of start a little bit slow by just doing some simplifications. So we have square root of 2a at the top and a 2a at the bottom. So this is going to give us like what? And you know, I left out the square here. So we have h bar squared over square root of 2a pi. And then we have 1 over square root of 1 over 4a squared plus h bar t over 2m squared. And then we're multiplying this by 1 over a plus 2I h bar t over m. And we have our integral from negative infinity to infinity of e to the negative x squared. And then what is this? This is going to be like 2 over a divided by 1 over a squared plus 2h bar t over m squared. And then multiplied by 1 minus 2x squared over 1 over a plus 2I h bar t over m dx. Okay, this is horrid looking. And you know what? I actually need a moment to reset myself, so I will cut this and be right back. Okay, I've reset myself and I've also gone one step ahead. Basically, I've taken this and I've moved it and I've expanded it into 2 integrals. And we're going to have to use sort of u sub and integration by parts to get the ERFs of both. So let's start with the easier one. So we're going to use u sub here. We're going to say, okay, u is equal to x times the square root of 2 over a multiplied by 1 over a squared plus 2h bar t over m squared. So du is equal to dx multiplied by this same thing, 2 over a, 1 over a squared plus 2h bar t over m squared. And if we do this, then this first part, and you know what? Let's label this by color. So I'll label this one in green, and I'll label this one in blue. So what's the green one going to equal? We're going to get the integral from negative infinity to infinity of e to the negative u squared times du times square root of 1 over a squared plus 2h bar t over m squared, all divided by 2 over a, because we take the reciprocal of this. And this is going to give us just square root of pi times square root of 1 over a squared plus 2h bar t over m squared, all divided by 2 over a. Now let's do the blue one, which is more painful. So let's see. What we have is 2 over 1 over a plus 2I h bar t over m times the integral from negative infinity to infinity of x squared e to the negative x squared times 2 over a times 1 over a squared plus 2h bar t over m squared dx, and we're going to use integration by parts, so we're going to say, okay, d by dx of e to the negative x squared. I really hate writing this out. 2 over a 1 over a squared plus 2h bar t over m squared. This is going to equal, let's see, negative 2 times 2 over a over 1 over a squared plus 2h bar t over m squared. And then we have an x term, and then we have e to the negative x squared times 2 over a 1 over a squared plus 2h bar t over m squared. So we can rewrite this as 2 over 1 over a plus 2i h bar t over m, and then we have this extra term at the front, so this is going to be what is this going to be? Negative 1/2 times 1 over a squared plus 2h bar t over m squared over 2 over a, because we take this whole thing basically and take the reciprocal of it to move it onto the other side, and we have an integral from negative infinity to infinity of x times d by dx of e to the negative x squared times 2 over a 1 over a squared plus 2h bar t over m squared dx. So then we use u sub. So u is equal to x, du is equal to dx, dv is equal to d by dx of e to the negative x squared times 2 over a over 1 over a squared plus 2h bar t over m squared. Writing is getting messier as I lose my patience for this. V is then equal to e to the negative x squared times, oh god, 1 over a squared plus 2h bar t over m squared over with 2 over a at the top. And then we switch this around and we do this whole thing again. So okay, first off, you can cancel these terms. So what we have left is 1 over a plus 2i h bar t over m with a negative in front, multiplied by 1 over a squared plus 2h bar t over m squared over 2 over a. Then we have our integral from negative infinity to infinity. So uv, which is, that just goes to 0, minus integral of v du. So the minus term cancels out with this minus term. Integral of v du, which is just e to the negative x squared times 2 over a times 1 over a squared plus 2h bar t over m squared dx. Then we do u sub again in order to get this into the form of a Gaussian. So u equals x times square root of 2 over a divided by 1 over a squared plus 2h bar t over m squared. So du is equal to dx times the square root of 2 over a over 1 over a squared plus 2h bar t over m squared. And we rewrite this out, and what do we get? We have the same stuff at the front, so I'm just gonna copy paste this. And then we have our integral. So this is gonna be, let's see, dx du. Yeah, so square root of 1 over a squared plus 2h bar t over m squared all over 2 over a at the front, right? Yes. And then integral from negative infinity to infinity of e to the negative u squared du. That's just going to equal square root of pi. So what we have finally is the square root of pi 1 over a plus 2i h bar t over m times 1 over a squared plus 2h bar t over m squared over 2 over a, and this whole thing is to the power of 3/2, where I'm combining these two terms. And with that, we have finished these two integrals. Now we have to go all the way back and rewrite everything from scratch again. So I will set this up and I will be back. Okay, so this is our final setup. And immediately, thankfully, I can start taking out a few things. So first off, there's the fact that there's this square root of pi that comes out of both. So I could just distribute those out and I can cancel it with the square root of pi down here. Next thing is I can factor out one of these, like a factor of 1/2 for this term, because these are kind of shared across both. So what we have now is h bar squared over square root of 2a times 1 over square root of 1 over 4a squared plus h bar t over 2m squared. And then we're multiplying by 1 over a plus 2i h bar t over m. And then we're multiplying by a factor of square root of 1 over a squared plus 2h bar t over m squared over 2 over a. And what we have left is 1 minus, and then this is a 1 as well. So 1 over a plus 2i h bar t over m multiplied by 1 over a squared plus 2h bar t over m squared over 2 over a. And now our goal is just to try to simplify things a little bit. So sort of really the only thing that we can do is just sort of try our best to combine a few terms. So let's start with that. So immediately, what I can say is I can combine 1 over a plus 2i h bar t over m into, let's see, m plus 2i a, well, let's do 2i h bar a t over am. Is that correct? M plus 2i h bar a t over am, yeah. So this is going to equal, well, okay, so this is number 1. Number 2, let's see, we have a square root of 2a times 1 over 16a squared plus h bar squared t squared over 4m squared. So we can condense those into a single thing, and this is going to give us like what? 1 over 8a plus h bar squared a t squared over 2m squared. So what does this finally give us? This is going to give us h bar squared over the square root of 1 over 8a plus h bar squared a t squared over 2m squared. And then we have multiplied by am over m plus 2i h bar at. And then we have this square root term, which is going to be like, let's see, 1 over a squared plus 4h bar squared t squared over m squared over 2 over a. And then we have 1, and then we have the same term here, 1 over a plus 2i h bar t over m. So this is going to give us minus am over m plus 2i h bar at, and then multiplied by 1 over a squared plus 4h bar squared t squared over m squared over 2 over a. Okay, next thing, let's try to sort of condense some of these. So number 1, we have 1 over 8a plus h bar squared a t squared over 2m squared. So what does that give us? If we combine these, this is going to give us 2m squared plus 8h bar squared a squared t squared. And then we have at the bottom 16am squared. Yeah. And then number 2, we have 1 over a squared plus 4h bar squared t squared over m squared, all divided by 2 over a. So this is going to give us like what? M squared plus 4h bar squared a squared t squared, all divided by a squared m squared, times, divided by 2 over a, so times a half. So this is going to give us 2m squared, or you know what, let's just do m squared plus 4h bar squared a squared t squared over 2am squared. So if we combine these, what are we going to get? We're going to get h bar squared times the square root of the reciprocal, or the reciprocal of the square root of this. So this is going to give us, let's see, the square root of 16am squared over 2m squared plus 8h bar squared a squared t squared. And then what else do we have? So that's this first term taken care of, and then we have am over m plus 2i h bar at, and then we have the square root of this thing, so square root of m squared plus 4h bar squared a squared t squared over 2am squared, and then we have 1 minus am times m plus 2i h bar at multiplied by this thing, which is going to give us m squared plus 4h bar squared a squared t squared over 2am squared. Close this off, and now we have a bunch of stuff that is kind of painful. So let's see. Immediately, I can cancel out some terms. am squared. The 2 can just go away and turns this into 8. So we have 8, and we have 1. What else? There's nothing stopping us from replacing this, multiplying this effectively with 2/8 over 2. There's nothing stopping us from doing that, in which case the top and bottoms cancel out as well. So this top and this bottom cancels out. So we're left with h bar squared, and then we have square root of 8 over 2, which is just square root of 4, which is just, so 2h bar squared times am over m plus 2i h bar at. Okay, that's looking a bit nicer. And then we have 1 minus, and let's see, we have am at the top, which cancels out with the am at the bottom. So this becomes 1 over, and then we have just 2m. So what is that? M squared plus 4h bar squared a squared t squared over 2m squared plus 4, well, maybe I don't want to completely do that yet. I guess I could, so let's just do it. Let's just get it over with. 2m squared plus 4i h bar atm. So if we combine these, this is going to give us 2h bar squared times am over m plus 2i h bar at multiplied by, let's see, 2m squared plus 4i h bar atm, and then 2m squared plus 4i h bar atm minus m squared minus 4h bar a squared t squared. And then what? We can cancel out, let's see. Yeah, we can cancel out 2. So the 2m squares make an m squared. So this is going to be 2h bar am over m plus 2i h bar at. And then we have m squared plus 4i h bar atm minus 4h bar a squared t squared over 2m squared plus 4i h bar a t m. And I am out of room, so I'm going to extend my canvas and I will be right back. Okay, final stretch. So a bit more cancellation that we can do. So first off, the 2 can cancel out with the 2 here and make a 2 here. We can also cancel out the m with the bottom. So the m here goes to m and like that. Okay, now let's see. This is pretty nasty. Also, I just realized I left out a squared on my h bar. Okay, so let's see. We have a h bar squared at the front, and then we have 1 over m plus 2i h bar a t multiplied by m squared plus 4i h bar a t m minus 4 h bar a squared t squared over m plus 2i h bar a t. So what this tells me, because we know the answer, Griffiths gives us the answer. His hint is that the expectation value of p squared is supposed to just equal a h bar squared. So what this tells me is that this sort of these two terms have to sort of cancel out. Everything here has to cancel out to just equal 1. So to show that, what I'm trying to do is I'm going to try to multiply these two together and see if that equals this numerator. And in that case, if it does, everything's nice and dandy. So this is gonna, what's this gonna give us? M squared plus 2i h bar a t m, and then plus 2i h bar a t m, and then minus 4 h bar squared a squared t squared. So this is going to give us m squared plus 4i h bar a t m minus 4 h bar squared a squared t squared. That almost equals this. I'm just missing a squared on my 4 h bar. That tells me that I made a mistake somewhere up here. So let me just double check. Plus 4im squared minus m squared minus 4. Yes, right here I left out the squared. So there is supposed to be a squared here. In which case, yes, indeed, everything is fine and dandy. This does just equal a h bar squared, in which case that is what the expectation value of p squared is. And with that, we are done, mostly. We still have to do the uncertainties, but we are done with sort of the painful part. Okay, final part of this last part, or the final, this isn't even the last part, but the final part of part D is we want to find the uncertainties in x and p. So these are pretty much trivial, especially compared to the hell that we had to go through earlier, but the uncertainty of any value a is just going to be equal to the square root of the expectation of a quantity squared minus the expectation of a itself squared. So we know that the expectation of x and p both are 0. So the uncertainties in x and p are respectively just going to be the square roots of the terms we just found. So the uncertainty in x is going to equal 1 over 2 omega, because square root of 1 over 4 omega squared, and the expectation, or the uncertainty in p is going to be h bar square root of a. We defined omega earlier, so this is, if we want to define this properly, this is going to be, let's see, 1 over omega is going to be square root of 1 plus 2 h bar at over m squared over a. So if we want to write this out fully as an actual sort of full fraction, we have to actually add these together. So this is going to give us like what? 1 plus, and let's write this out fully. So 4 h bar squared a squared t squared all over m squared, all divided by a. Is that correct? 4 h bar squared a squared t squared all over m squared. Yeah. This is going to give us, let's see, m squared over m squared at the bottom, and then at the top we have m squared plus 4 h bar squared a squared t squared, and then all of this is divided by m, so, or divided by a, so we just might as well just write a in the denominator and get it over with like that. This is a horribly ugly square root, so let me just correct that real quick. And then we have a 1/2 attached to the front, so the uncertainty in x is just 1/2 times the square root of m squared plus 4 h bar squared a squared t squared over a m squared. And if we want to make this condense this even further, if you will, we can turn the 1/2 into the square root, in which case this is going to be over 4am squared. Let me just double check that I am actually correct and not going insane after everything that I just had to solve. Okay, that is correct. And then the uncertainty in P is as is. So next, we are going to do part E, which is very short, thankfully, and then we will be done with this horrible problem. Okay, part E. Does the uncertainty principle hold? And at what time t does the simple system come closest to the uncertainty limit? So the uncertainty principle is just that the standard or the uncertainty in x multiplied by the uncertainty in p has to be greater than or equal to h bar over 2. This is something we went over back in chapter 1. So we check this, or we can just check this. So square root of m squared plus 4h bar squared a squared t squared over 4am squared, and then multiplied by h bar times square root of a. So instantly we have a square root of a at the top and a square root of a at the bottom, so those can just cancel out, and we're left with 4m squared at the bottom, and we have an h bar at the front. And if we look at this, the only t dependence is right here in this term 4h bar squared a squared t squared. If we want to minimize the uncertainty, then we want the numerator to be as small as possible. So that means t equals 0 is the smallest possible uncertainty. So at t equals 0, uncertainty is minimized. So at t equals, sigma x, sigma p at t equals 0 is going to be equal to the square root of m squared over 4m squared multiplied by h bar, or just h bar over 2, which is indeed exactly equal to the lower limit of the uncertainty principle. In contrast, at the higher end, where t goes to infinity, the uncertainty goes also to infinity. And that sort of does agree with what we found earlier when we graphed it, because we found that sort of the initial graph of psi of x comma sort of psi of xt squared, or magnitude psi xt squared, I should say, looked kind of like a Gaussian. It was this very sort of nice Gaussian curve. And what we found is that as t went to infinity, this gradually flattened out into just a flat line along the x-axis that was at x equals, or at y equals 0 always. So it makes sense that in this case, since it's equally likely to find the particle pretty much from negative infinity to infinity, its uncertainty in x would also be infinity, and its uncertainty in momentum would also probably be infinity as well, for the same reason. So because of that, the resulting sort of uncertainty principal value is going to be infinity correspondingly. And with that, we are finally done with chapter 2.4, and we can move on to the delta function.